much. Well, firstly, I would like to acknowledge the traditional custodians of this land, the Wathaurong people and elders past and present. And this paper is something that I'm interested in, and you might like to hear about it, but the content is not typical of what I'm teaching. I don't really sort of expect this much of the particular student cohort, so to speak, and I'll offer a little disclaimer. Please remember I'm in history rather than science, and my mathematics, especially in terms of mental arithmetic, is pretty horrible, so if I make any errors, please feel free to correct me at the end. The key issues we'll be discussing will be weapons of mass destruction and disarmament, although I might speak with a clear interest in the underlying principles, and sometimes in a fairly jovial tone, do rest assured that I do appreciate the gravity of the matter and the horrors of nuclear weapons. For instance, I question very strongly the alleged deterrent value of nuclear weapons and the prevailing theory that the threat of mutually assured destruction kept the peace during the Cold War and stopping the Cold War from turning hot, because if you look through the history of those years, you can see several occasions where things very nearly turned very dire indeed, and good management had a lot to do with it, and good luck. So tonight I'll be discussing the links between weapons research and how we come to understand the universe itself, especially matter. I will try to avoid, if possible, taking any questions at the end about Fukushima, and instead discuss how the work of one individual sits outside mainstream perspectives on these matters, and discuss also the role of fictional, pop cultural and artistic sources and the significance of the internet in the contemporary age. So putting this presentation into the realms of cultural studies. So who is, and I do also hope I'm pronouncing his name correctly, Dr. Gsponer? Well, he is a former research fellow at the European Organisation for Nuclear Research, or CERN, and he has interest in weapons of mass destruction and disarmament. Now, in the spring of 1979, he was working on an experiment where a key part of the apparatus was a toroidal or donut-shaped magnet. A colleague of his, Klaus Freudenreich, had reported that a guest, who was an engineer from Iraq, was asking a series of probing questions about this magnet. Now, to appreciate the significance of this magnet, some background information is indeed required, and this particular part of the story concludes in Iraq in 1991. But in the beginning, there was the particle accelerator. Now, such apparatus have been key to our present understanding of the natural world, and unfortunately have featured in our understanding of perhaps how we might destroy it. Some of you may recognise the title of this presentation, Talking Moonshine, as a quote from Ernest Rutherford, who stated, incorrectly as it turns out, anyone who looked for a source of power in the transformation of the atom was talking moonshine. Now, one of today's goals is to explore whether Gsponer himself was talking moonshine, but regardless of that, I think you'll agree there's some interesting stories to tease out. Now, Ernest Rutherford, he was the recipient of the 1908 Nobel in Chemistry for his investigations into the disintegration of the elements and the chemistry of radioactive substances. And a key part of Rutherford's work was the discovery that one element can be transmuted to become another, a sort of new nuclear alchemy. Now, with Frederick Soddy in 1919, using an accelerator, he fired alpha particles at nitrogen atoms and effectively created oxygen. Well, it wasn't the first instance where oxygen had existed, but it was the first example of a nuclear transformation. And another key discovery occurred in 1932 when a colleague of his, which was James Chadwick, discovered a type of particle known as a neutron. Though this discovery was vital for understanding the natural world, this finding would also be linked to the horrors of Hiroshima and Nagasaki and the arms race to follow. As neutrons have no charge, they are not repelled away from the nucleus of an atom, and in certain materials this process here can occur, a nuclear chain reaction. So this is simplified but close enough. The bundles we pictured here are nuclei. The red dots are protons. They have a positive charge and wish to repel away from one another like the light charged poles of a magnet, but they're bound together by the strong nuclear force. When they're impacted, or well, when a neutron is drawn close enough together to be attracted by said force, the shape of the configuration changes, and this electromagnetism wins this tug of war between the fundamental forces, and they break into fission fragments, and there's a yield of energy. Each fission yields about enough energy to make a grain of sand or a speck of dust visibly jump, which doesn't actually sound like a great deal, but when you put this into context, that's actually pretty staggering. As this graphic from IFL Science depicts, admittedly this is not a uranium atom, it's a smaller atom, looks like a lithium atom, but a speck of dust is halfway between the size of an atom and the planet on which we stand. So when the nucleus is split, you see enough energy yielded to make that visible speck of dust jump, and there they're drawn to scale. And of course, this process occurs over and over and over in this chain reaction. Now, to explore this kind of rapid growth, you could do an experiment in folding a piece of paper in half. There's a very finite amount of times you can actually repeat that process before you can't actually fold it anymore, this sort of rapid doubling. As the Wolfram Alpha computation app for iPhone depicts there, you can't really probably see it too well, but you're seeing an energy yield of, per average uranium-235 fission, of 200 megaelectron volts, and that is equivalent to the mass of 1/5 of a proton being expressed as energy. Just for some comparison, in the uranium-235 nucleus, where most of the mass of an atom is, there's 92 protons and 143 neutrons. But it's wrong to consider that in terms of that mass being the sum of the parts. And of course, this process occurs over and over and over. You may have heard the word critical in the context of weapons and so forth thrown around. Reactors go critical. Within a nuclear bomb, there's a critical mass, and if you were to shovel enough enriched uranium together into one place, it would too go critical, and your last weeks on Earth would be rather unpleasant. But what is criticality? Now, this diagram here is not a literal representation of what's actually occurring inside the pit or the central core of a nuclear weapon, because that's a three-dimensional space. But just consider contrasting the idea of what is happening now in the system with what has previously taken place in terms of generations. So criticality is essentially growth in the neutron population. There's a constant known as K, which is the multiplication constant. And if there's more neutrons present in the previous generation than there were in the current generation than there were in the previous, it is critical. Within a reactor, you use a moderator to slow the neutrons down to a particular speed. Excess neutrons are absorbed by control rods, and this constant is kept, or usually at K itself, so it's just critical. And the heat is utilised for power generation or as a neutron source for transmuting elements and so on and so forth. Where are we? But if the systems have a particular, if the materials involved have a particular property, a fast system can create it. The result is an uncontrolled nuclear chain reaction. Such materials are known as fissile, and the result of such a fast reaction may be a criticality incident, but if the system really gets going, you're going to see a nuclear explosion. So fissile means able to sustain a chain reaction without a moderator. It means that material can be fissioned or split by neutrons of any speed or energy. Fissionable means able to undergo fission. So this might take some explaining. All fissile material is fissionable, but not all fissionable material is fissile. And that's a concept sort of worth repeating because it's often misunderstood on the literature of surrounding disarmament. So fissile material is able to self-sustain this kind of rapid chain reaction. But fissionable material means that the atoms can be split with a high energy neutron. It is possible, for example, to split the atoms of uranium-238, unenriched uranium, and indeed that process is central to the very largest types of nuclear weapons ever designed, the fission-fusion-fission configuration. So within a fission weapon, this critical assembly takes place. Sufficient fissile material is brought together at high speed, or alternatively compressed together to reduce the mean free path, which is the average distance a neutron may travel before striking or being drawn into a nucleus. And the result is a multiplication factor, or K, greatly exceeding 1. You might see K between 2 or 3. In weapon-specific parlance, the neutron multiplication rate is known as the alpha. So if you see suspicious-looking folk discussing the alpha and enrichment, please kindly inform the federal police. Now, one of the suitable materials is a light isotope of uranium, uranium-235, which is very tedious and expensive to separate out. And one means used during the Manhattan Project was something known as electromagnetic isotopic separation. Ernest Lawrence and others modified a type of particle accelerator known as a cyclotron to become a type of mass spectrometer, which they nicknamed the calutron, coming from University of California cyclotron. It was used to separate out the lighter isotope. So the famous story goes, they were lacking the requisite copper for the electromagnets there was a war on. They apparently turned to using silver from the treasury, returning it after hostilities ceased. Of course, silver and copper in the same periodic table group. This process worked, but was expensive and difficult and inefficient. It was expensive even utilising copper as opposed to silver. So all the materials surrounding this process were declassified and became open source. Flash forward to 1979 and that Iraqi engineer asking questions about large magnets. As it happens, Iraq was adopting the same technology under Dr. Jafar for their nuclear weapons program. Their calutrons were destroyed in the 1991 conflict, and their reactors had been destroyed years earlier by Israeli airstrikes. And this discovery of enrichment technology was touted as a huge surprise by Western intelligence analysts. But Gsponer and his colleagues had been attempting to publish their suspicions about this way back in 1980, in the proceedings of the Non-Proliferation Treaty Review Conference, in the Journey Science and Technology Review, and of course in the famous Bulletin of Atomic Scientists, without any success, more or less ignored. Now, I had first became aware of Iraq's enrichment program through this thriller novel. It being fiction, details the Americans accidentally destroying this complex at Tamir and having to figure out what the calutrons were. An elderly engineer is approached and shown photographs, and he asks, "Why are you showing me photos of Oak Ridge?" And that was the site in Tennessee where calutrons were housed during the Manhattan Project. In reality, the Americans hadn't forgotten about electromagnetic isotopic separation, though one does wonder why the warnings of Gsponer and his colleagues had not been heeded. Now, this author, Frederick Forsyth, in his early years of writing, was somewhat notorious for filling his novels with fact-based content and offering insight into the reader as to where fact and fiction deviated. He was censured at the time of the publication of the novel The Day of the Jackal for providing a means for persons to obtain false identity documents, although that particular loophole has now been closed. I recount this as an example, linked to cultural studies as it is, of how creative works can assist a readership to gain an understanding of real-world issues in cases where the differences between fact and fiction is signposted. And there's been a substantive debate around this in the history discipline, for example, related to Kate Grenville's novel The Secret River and its commentary on massacres of Indigenous Australians and the resulting debate about the role of historians and writers of fiction. Actually, as it happens, I had been reading that novel in 2003 and pondering the history of Australia's relations with its great and powerful friends, and Australia was poised to assist the US in another military campaign in Iraq. And the result of this musing was me having a conversation with Jeremy Smith, enrolling in an honours year and leading directly to you having to endure my seminar tonight. But returning to weapons of mass destruction. Before they were the subject of serious research, nuclear weapons were included in the plot of H.G. Wells's novel of 1914, The World Set 3. Powerful weapons are, of course, a standard feature of science fiction, and this is significant in regards to tonight's discussion. I'm sure that some of you are going to be thinking that this next part is absolute nonsense, but please keep listening and sort of weigh it up. In our universe, there exists something known as antimatter. It is simply matter with an opposite charge. For example, electrons have a negative charge, and thus anti-electrons are known as positrons. The occurrence of antimatter is commonplace. In our bodies, there's the isotope potassium-40, which undergoes all three kinds of beta decay, producing electron antineutrinos, for instance. Also, hospitals make use of something known as a PET scan, which is positron emission tomography. Now, antimatter comes up a lot in science fiction. The reason being that when particles and antiparticles collide, their combined mass is expressed as energy, the entirety of it. Compare and contrast that back to the early discussion of a fission reaction where it's 1/5 of a proton mass being expressed as energy. We're talking about the whole lot. So those of you who have read their fair share of science fiction, you will see antimatter being utilised to destroy whole planets or power starships to the distant reaches of the universe. Now, Gsponer has written a great deal about the possible military applications of this energy. And this is a subject that CERN hates, And this is partly at least the fault of a reasonably poor quality novel. In this novel, a group of terrorists known as the Illuminati steal a quantity of antimatter from CERN and intend to use it to blow up the Vatican. In response, CERN has made numerous statements and devised a section of their webpage debunking the plot of the novel and the use of antimatter in weapons, stating that it's simply too expensive to produce and contained for it to be weaponised. CERN has stated that their entire antimatter production so far could yield enough energy to run an electric light bulb for a few minutes, and they state that trapping whole anti-atoms is prohibitively difficult for the most part, and that light-charged particles such as positrons require a great deal of energy to contain because they wish to repel away from one another, and of course they can't come into contact with each other. Irrespective of the issue of containment, NASA continually throws around the figure of $62.5 trillion per gram for antimatter. That's 625 followed by 11 zeros. Let's have a look at what 1 gram of antimatter and 1 gram of matter annihilating would look like in terms of relativistic energy. So we see here the figure in joules, according to Einstein's famous mass energy equivalence equation, and expressed here in thousands of tons of TNT. So 2 grams of relativistic energy, you're looking at approximately 41.3 kilotons, or 1/58th of the energy involved in forming the meteor crater in Arizona, or approximately 1/3 of the energy released by a hurricane in 1 second. For comparison, the device which destroyed Nagasaki had a yield of approximately 22 kilotons of TNT. So as you can see here, in terms of a weapon system, that would be somewhat of an expensive process. The Manhattan Project cost $2 billion in 1943 currency. But using antimatter alone as a weapon is not quite what Gsponer and his colleagues have been talking about. But once again, we need to go back in time. The first nuclear weapons of the type employed against Hiroshima and Nagasaki were pure fission bombs, but there's the next generation are those which derive a portion of their yield from a fusion reaction. Now, one of the features of our natural world is a phenomenon known as the curve of binding energy, and with it the iron peak. For atoms heavier than iron, there's a net yield of energy when the nucleus is fissioned. For elements lighter than iron, there is a net yield when they are sort of fused together. Where are we there? They wish to repel away from one another, these light-charged hydrogen nuclei, as per the like-charged poles of this magnet. A common analogy, though, is imagine that the poles of these magnets are covered with a very, very strong glue. They wish to repel away from one another, and when they're forced into close proximity, they stick. And there's an energy yield. And this takes tremendous pressure to achieve, and this is typically being done using nuclear fission. In a hydrogen bomb, for example, there's a fission primary stage driving this reaction in a fusion secondary. And weaponeers would love to devise a pure fusion bomb for several reasons. Firstly, thankfully, fissile material is very costly and difficult to obtain. And there's also a definite lower limit to the size of a viable critical mass needed for a nuclear explosion. And of course, fission weapons also produce considerable amounts of fallout in the form of unfissioned material, which is the atoms that don't get split, and fission products, which is the atoms which have been split into typically short half-life, very radioactive substances. There's a popular misconception that nuclear weapons have continually grown in destructive capacity, but they actually peaked in 1961. Delivery systems got more accurate, better missiles, faster bombers, and so on and so forth. And Cold War strategy, should it have turned hot, shifted away from a strategic doctrine of counter-value, the targeting of cities, towards counter-force, targeting leadership and their retaliatory capacity, sort of in the parlance to cut the head off the snake. Now, the latter years of the Cold War saw proposals and in some cases developments of highly specialised third-generation nuclear weapons for particular purposes. Gsponer himself weighed in on the public discussion surrounding the idea of the robust nuclear earth penetrator, or the nuclear bunker buster, which in theory would bury itself to the extent in the earth that it would destroy subterranean targets without the resulting fallout venting into the atmosphere much. Now, what Gsponer weighed in on this discussion, and one of the products of the exchange was a concern about the idea of plutonium mining, which is sort of a counterintuitive thing to consider because plutonium is a human-made element only found in trace quantities in nature, so how do you mine for it? Well, you scrape it out of the ground after someone's used it to try and blow you up, is effectively the problem. So it actually resulted in a public discussion that if you're going to build nuclear bunker buster bombs, they're actually going to scrape the material out of the earth afterwards and reuse it. And that says a great deal, I think, about just how costly this material is and how difficult it is to obtain, like the sort of levels that people would go to. Now, according to the journalist John McPhee in his book, The Curve of Binding Energy, taking its name from the previous graphic, Theodore B. Taylor, who was a weapons designer, proposed the idea of something known as MICE, or megaton ice-contained explosion, burying a hydrogen bomb underneath a gigantic ice cap, wrapping the whole thing in uranium and using it as a neutron source to breed more plutonium. The fact that this is actually thrown around suggests just how much people want to get their hands on this material. Taylor's an interesting subject, along with Freeman Dyson, who was reportedly the inspiration, at least for the name, of the scientist Miles Dyson in the Terminator films. He worked on Project Orion, which is the proposed use of nuclear explosives to power spacecraft. And apparently Werner von Braun himself had been very impressed by this proposal. Taylor is also the first person and the only person to ever, utilising a parabolic mirror, and his back to the flash, to light a cigarette with a nuclear bomb. That actually happened. His test was delayed, he's walking around, and yeah, he scraped together some apparatus and turned his back to the blast and used the focused thermal energy to light a cigarette, which is just strange. Generation 3 nuclear weapons included man-portable atomic devices and nuclear artillery shells. And once again, there's a definite lower limit to a viable nuclear weapon, and this is usually referred to as the tyranny of the critical mass. Now, to my knowledge, the smallest type of nuclear weapons yet devised employ the two-point linear implosion principle. And this is a little bit counterintuitive. Now, the bomb that destroyed Nagasaki, featured here, it had a bulky array of explosive lenses, which triggered an initiator at the very centre of the weapon. An initiator is like a neutron source, and compressed a 6.2 kilogram sphere of plutonium, decreasing that mean free path and bringing the system supercritical, and it yielded 22 kilotons. Now, in this very small and now obsolete W48 artillery shell, approximately 155 millimetre by 838, the pit was an ovoid configuration. And rather than a bulky array of lenses, you're seeing explosives at either end. And when triggered, they would compress the ovoid across its major axis, presumably triggering an initiator at the same time, and just enough fission generations occurred for a 72-tonne yield. So to put that in comparison, in the 70-year-old Nagasaki design, 6.2 kilograms of plutonium yielded 22 kilotons. In this, approximately 13 kilograms of plutonium, so double the amount, producing 72 tonnes, and of course scattering unfissioned material everywhere. And this serves to sort of illustrate the kind of lengths that people in the United States and in the Soviet Union were going to develop small nuclear weapons which could secure discrete objectives. Now, one of Gsponer's major concerns is not like an earth-shattering doomsday weapon, but something very, very small. Here's a simple diagram for something he's termed a type of fourth-generation nuclear weapon, a small fusion bullet in which the fusion of heavy hydrogen, you see here the letters DT denoting deuterium and tritium, is driven from an outside source, perhaps by antimatter annihilation. So we see this 1 centimetre core being surrounded by a small triggering mechanism, and when triggered, this would yield approximately 1 tonne of energy. Now, equivalent to TNT. So, sorry, to clarify, equivalent to 1 tonne of TNT. The significance here is twofold. disarmament protocols like the report of the Canberra Commission on the Elimination of Nuclear Weapons rely heavily on the principle that they're too powerful to hold practical military utility, overkill nuclear weapons. Also, the Non-Proliferation Treaty, which is perhaps the most significant disarmament incentive, also relies very, very strongly on the control of special fissionable material, and you could read that as fissile material. So in reference to somewhat less likely idea of a pure antimatter weapon, where it's the annihilation driving all the explosive energy as opposed to using the principle to drive another reaction, Gsponer stated this: "It turns out that this possibility has been popularised by a highly successful novel, Angels and Demons, in which a terrorist organisation called the Illuminati is threatening to destroy the Vatican with 1/4 gram of positrons from CERN," and so on. As a result, this novel has succeeded in getting millions of people to understand that a new generation of nuclear weapon was scientifically possible, therefore stating some kind of public discussion on the prospect of such weapons. The irony is that this is precisely one thing I've been trying to do for the last 20 years without success. Other possible fourth generation nuclear weapons discussed by Gsponer include fusion derived from heavy ion beams or magnetic or laser confinement fusion. Now, to state this again, because this is an important element of this discussion, fusion driven by antimatter may well and likely will remain in the realms of science fiction, but it may not. But eventually it would seem likely that some yet unperfected means fusion weapons could be constructed which require no fission primary stage. And this is what Gsponer and others have written about extensively. Now, those following developments in fusion are aware that the relevant experimental apparatus for fusion driven by such means as laser arrays and magnetic confinement, they're not yet capable of yielding as much energy as they use. Considerable media attention resulted when Lawrence Livermore's National Ignition Facility reached a point where fusion energy from a deuterium-tritium pellet exceeded the total amount of laser energy that the pellet had absorbed, but not exceeding the amount of energy required to power the laser array. So to say that again, from the fusion reactions, they're seeing more energy out than has actually been absorbed by the pellet, not exceeding the amount of energy which is required to power the apparatus. Now, for those that are dreaming of a free energy utopia, as this slide from Livermore details, one key aspect of their program is not green energy, it's weapons stockpile stewardship. The United States stopped testing in 91 or 92, and they have the enduring stockpile. So they wish to replicate the conditions of a hydrogen bomb explosion through fusion research as a means to maintaining their weapons in a usable condition. Further to that, arms manufacturer Lockheed Martin, I'm sure you might have seen this story kicking around in the press recently, they received considerable media attention with their claim that their secret Skunk Works research group may be able to produce a truck-sized practical fusion energy facility within a decade. And this claim has been met with some scepticism. So tonight's presentation has been a brief exploration of some of Gsponer's concerns and a glance at where science fiction may meet with scientific fact, and of course how such issues are framed and perpetuated. Though the idea of antimatter bombs or even antimatter-driven fusion bombs is presumably still far-fetched, and the response from CERN to the issue is interesting, as was Gsponer's attempts to bring Iraq's electromagnetic isotopic separation program to the attention of the international community. One of the key sources for tonight has been the Nuclear Weapon Archive. I can only hope I haven't garbled the technical details too much. And some of what I've been discussing may seem pretty far-fetched. I'm certainly not saying lock up your positrons, merely discussing an aspect of the public conversation and the work of one particular figure whose perspectives are outside the mainstream. So, in addition to what Ernest Rutherford stated of talking moonshine, consider what Einstein himself also once stated on the practical application of the possibility of expressing mass as energy. The likelihood of transforming matter into energy is something akin to shooting birds in the dark in a country where there are only a few birds. Thank you very much.